Determining the lighting conditions in a scene is an important part of many problems in computer graphics. Consider a simple closed two-dimensional scene, a room with 4 diffuse walls. If there were some number of isotropic point lights in the scene, then the resulting direct lighting along the walls would look like this. Now we ask the question, using only the direct lighting on the walls, can we figure out the number and locations of the point lights? We present a framework for solving this light localization problem consisting of a novel spatial transform to propose candidate light positions and an iterative algorithm to refine the light parameters.
Let's start by looking at a surface patch on the wall. Say we hypothesize that there's exactly one light in the room at point X. What does our patch tell us about this light? Based on the patch's brightness, orientation, and distance to point X, we can directly calculate the intensity of this hypothetical light. Plotting this intensity for every possible light position gives us the intensity function for that patch. But this only tells us the potential intensity of a single light in the scene. What if there are multiple? A patch could be illuminated from several different light sources, so we cannot calculate the exact intensity coming from some point. However, at any given point, a single light still cannot be brighter than a patch's intensity function. In other words, the intensity function gives an upper bound on the light intensity at every possible position. This gives us a useful way to combine the intensity functions for every patch in the scene. We take the minimum of the intensity functions at each point to get the most restrictive upper bound. This gives us the intensity distance field, or IDF. We can observe some IDFs calculated for different scene conditions, such as varying light source positions, varying numbers of lights, different scene geometries, and scenes with occlusions. From these observations, a pattern emerges where lights frequently lie on the medial axis of the distance field. We use the IDF to help us narrow down the points where the lights are most likely to be located. Recall that the IDF is calculated from the minimum upper bound at each possible light position. We can determine which patches correspond to those minima and map each point to the patch that limits its intensity the most. The result is the limiter field. We can visualize the limiter field by assigning each patch a color and coloring the points that are most restricted by that patch's brightness. With the limiter field, we look for positions where many patches agree on the potential intensity of a light. These patches are likely lit primarily by a single light source, so they vote consistently on the intensity and position of that light. Counting the number of unique limiters in a small region therefore gives us our voting function. The peaks in the voting function then give us candidate light positions. However, because of the underlying single light assumption, the voting function does not always give all the light locations, nor are all the positions always accurate. To correct for this, we use an iterative refinement approach. We maintain a rough hypothesis for the position and number of lights in the scene, starting with the output from the voting function. We also assign an intensity to each light, starting at 0. Each iteration, we increase the intensity of some lights, refine their positions, and compare the resulting illumination with the original input. Based on the remaining illumination that is still unexplained by our hypothesis, we can then recompute the voting function. This algorithm gives us a rough estimate for the lighting, which we periodically use to initialize a nonlinear optimization for the position and intensity of the lights. Here we can see how the voting function and hypothesis evolve during iteration. 2 lights are detected quickly, followed by a third. The position of the lower right light moves towards the ground truth, and finally the 4th light is discovered, at which point the optimization succeeds. Our method extends itself to 3D scenes, where the IDF is defined over a volume. We visualize the voting function on the medial surface, where the maxima similarly correspond with light positions. We also show that our method works on real-world scenes, which include noise and interreflection. Here, our initial voting function gives us the location of one light, and after a few iterations, the other light is discovered as well.